Hello, this is Terry Kuzma here at Penn State University. What we'd like to go over today is part of our materials engineering, bottom-up manufacturing. What we're going to look at is techniques and driving forces for bottom-up manufacturing. So basically, what we're going to review is techniques that are popular in self-assembly. So what we're going to do in the first lecture is we're going to define what bottom-up manufacturing is, and we'll take a look at things like self-assembled monolayer, functionalized materials, and the Langmuir-Blanchet films. Part two, we'll probably start at and look at the surface energies, et cetera, and the bonds that are necessary to do that work. So we'll see how far we get, but I think we'll get to the Langmuir-Blanchet, and that'll be enough to end this particular lecture and start on part two. So let's look at this and describe what we're doing. What is bottom-up manufacturing? Bottom-up manufacturing, we can look at, one term is it's basically self-assembly. It's done by enabling a precursor on the substrate and encouraging controlled growth. For this lecture, we'll concentrate on particle to surface interactions. So let's take a big picture look and see about the energies that are driving the process. So SAMs are targeted for a specific precursor material, and again, this is a self-assembled monolayer. Early stages of adsorption on a target material is random and disoriented. The final monolayer consists of close-packed molecules with uniform orientation. The transition from early absorption to continuous monolayer is a stepwise process. And generally, this takes a finite amount of time, and it's dependent on the material. But we usually gauge this with, for most circumstances, I read that it would be on the order of minutes that this takes place. So general steps for self-assembled monolayers. Initially, we'll absorb molecules from a dilute two-dimensional vapor. This low density of mobile molecules randomly adsorbs to the target surface. An immediate density of adsorbed molecules produces a variety of orientations of the molecules on the surface. So we'll have islands of solids will nucleate and then grow on the target material. The final high-density phase consists of a continuous, closely packed, highly ordered conformal layer of molecules on the surface. This process follows the nucleation and island growth and coalescing that we're familiar with in two-dimensional thin film deposition. So this is what it looks like, a schematic drawing. We start out with these self-assembled monolayers. One side has a chemical preference for this material. The other side doesn't. So basically what we're going to do is have the ability to preferentially coat using, in some senses, we'll call this the head to the surface. So some popular examples, organosulfur compounds on gold are probably the most popular self-assembled units, at least that I read about in literature, and these are called alkthiols. And these are very well understood. There's different versions of this alkathiol, and what these alkthiols form, or what they offer, is different energies at the surface. So naturally, if we have more than one sulfur head or bond at the surface, we're going to be able to bond better than a single head. So this is a single head on here. This is a di, so this would have two. And then we could also have this as a disulfide, one head with two tails. So there's a variety of geometric complexities that we can look at for this basic process. But basically, as a thiol, what we're terming this is a polymer tail, a fatty acid tail, on a sulfur head. So let's look at the central mechanism for alkthiols. It involves strong interfacial binding of sulfur to gold and comparably strong lateral interaction between hydrocarbon chains. Alkthiols absorb spontaneously on gold surfaces from the solution and form alkathiolates with loss of hydrogen. The support for hydrocarbons is accomplished through cumulative van der Waals forces between the fatty chains, which can be functionalized to provide a desired material property such as wettability and protection against corrosion. Or we can cross-link those fatty acid tails with other biomolecules per se for some functionalized drug. So this is some examples of self-assembled monolayers, and we can look at the basically the energy in kilojoules per mole for these different types of materials. So the amount of energy needed to physiabsorb an alkathiol to gold surface increases as the size of the hydrocarbon increases. The amount of energy needed to chemabsorb the alkathiol to gold surface stays relatively constant as the size of the hydrocarbon increases. This should be expected since sulfur is responsible for the chemabsorption and really not the hydrocarbon itself. So we can take a look at the energy factors here and look at these graphs over the range of temperature and the relative intensity at the adsorption of the material. So I can let you review those and take a look at the peaks and see how they're necessary. So this is at, degrees in Kelvin. So many factors influence the tilt of the carbolic acid monolayers on surfaces. So if we would take a look at this, we have a carbolic acid interface right here, and what we're looking at is the bonding forces on the surface. So right here what we have is the surface itself, this being a silver oxide and this being aluminum oxide. What we have is the same we have the same thiol, the same carbolic acid system that we're trying to introduce to the surface, and basically due to the surface energy of these two, the difference between these two materials, we're actually going to get a different conformal layer or different geometry of the fatty acid tails on these materials based on the interaction of the head area with the parent surface material. So here's some applications for self-assembled monolayers. These can be used for communication between redox active enzymes and electric surfaces. This table summarizes various glucose enzymes produced from a variety of bacteria and various functional groups that link the enzymes to metal electrodes. So this is a handy chart that gives you the ability to link these enzymes to a surface to make, for example, some type of biosensor. So another popular method that we use for self-assembly is called the Langmuir-Blanchet film, and this has been around since the beginning of the 20th century. That's when it was pioneered by the husband and wife team. And basically, we use this quite a bit in different types of applications. I think the coating on windows is probably the most prevalent application, but I don't know if I'm expert enough to say that, but that's what I read quite a bit. And for certainly, as far as value added or a common material, that certainly is a nice application. So let's describe what this is. Langmuir-Blanchet film contains one or more monolayers of an organic material deposited on the surface of a liquid onto a solid by immersing the solid substrate to or from the liquid. A monolayer is absorbed homogeneously with each immersion or immersion step. Thus, films with very accurate thickness can be formed. So this is kind of like atomic layer deposition, but in the wet solution. And basically what we do is a dip. And every dip, what happens is this monolayer is going to form onto the surface. So again, this is really nice. This is certainly interrogated by people in solar cells to control the thickness of the interface on a solar cell. So Langmuir-Blanchet films are named after Irving Langmuir and Catherine Blanchet at General Electric Research Development. The work was done in the late 1920s. It's similar to atomic layer deposition, as I mentioned. A monolayer is absorbed homogeneously with each immersion step. The total film thickness is predictable because the thickness of each monolayer is known and can therefore be added to find the total thickness. These monolayers can be transferred to many different substrates. Typical substrates include silicon, silicon dioxide, glass, metals with oxidized surfaces. Naturally, the surface must be contamination-free. Substrates that have high surface energy, such as gold, attract contaminants and result and result in low quality Langmuir-Blanchet films. So this is the vertical deposition method, and represented by this color, I guess gold here, as far as I see what it looks like. We have an aqueous solution below this line, and basically what we can do is draw the substrate through the surface tension, or we can insert the material through the surface tension. So like we said before, this can take place when we dip the material in or pull the material out of the media. So what we're doing is we're taking advantage of the different energy levels between the surface, the air, and the water interface. And what's going to happen at this interface, what we're going to have is the surfactant molecules are going to line up on this air interface. So the nonpolar tail is going to be certainly scared or repulsed by the water, and the polar head is going to be immersed in the water. So we get this deposition layer formed on our deposition interface, the water to surfactant molecule interface. So what we'll have to do is define some of these things more, like what a surfactant is. A surfactant is a surface acting agent. These are compounds that lower the surface tension between two liquids or a liquid and a solid. Surfactants are usually referenced to an aqueous environment, or are made from organic compounds that are amphiphilic. That means both contain both hydrophobic end and a hydrophilic side. The term amphiphilic substances are soaps, detergents, lipoproteins, liposomes, and micelles. Further, an amphiphile is a molecule that's insoluble in water. This stability may be based on pressure, heat, or other energies such as light. This may cause the amphiphile to perhaps degrade. So the amphiphile is described under a steady state condition to where it's not harmed by the ambient conditions. The solubility of the amphiphile molecule in water depends on the balance between the alkyl chain length and the strength of the hydrophilic head. So therefore, surfactant contains both a water insoluble or oil soluble component and a water soluble component. Since the tails are hydrophobic, their exposure to air is favored to that over water. Similarly, since the heads are hydrophilic, the head-water interaction is more favorable than the air-water interaction. The overall effect is a reduction of the surface energy, or equivalently the surface tension of the water. So this was shown in an early experiment done by the famous Ben Franklin, and what he did is took a teaspoon of oil and he put it on a pond, and he actually saw that would actually change the surface tension. And what it did is it calmed the water on a half-acre pond. And in fact, this example was used later to prove Avogadro's number. So I think that's a real interesting part of history, and kind of neat what these people did at that time frame. So hats off to Ben Franklin for that. So this is another common form of a surfactant, is the lipid. And of course, we've looked at this in the bottom-up manufacturing course so far as the liposome for targeted drug delivery. So this is certainly one form of surfactant that we could use in our work. So this shows the lipid as a surfactant. So we have the hydrophobic nonpolar tails and the polar head in the water. And again, we could use this to initiate the Langmuir-Blanchet process by dipping some material in there that would preferentially target the heads to the surface. So this is some properties of different head groups. So if we would take a look at the different heads, we can describe whether the strength of them as a relative amount of energy. So in the very weak column, we have those weak and strong and very strong. So we can take a look at that, and that comes from one of the books that we use in the course is listed below, the Nanostructures and Nanomaterials. And that's from 2007. I think there's actually an updated version. I'd have to find it here on my desk, but I think there's a newer version in that from a little bit later on, I think 2011, 2013 or so. So this shows, again, the Langmuir-Blanchet film, and what we're doing mechanically here is we're compacting these to get a dense mono layer on the surface. And then we can look at the Schaefer method, and the Schaefer method is actually used to transfer monolayers from a water-air surface to a flat surface. So basically what we do is we would have this surface, and we do the compacting, and then we take another area right here, as shown in this black in this area, and what we can do is basically touch this to the tails, and we're able to lift that off by the tails. So this is a way of transferring this material not from the head surface but from the tail surface. So that comes in handy to use the other side. I think the most common example is when we're doing plating to the heads, but this shows plating to the tails. So one thing that we have to avoid when we're looking at Langmuir-Blanchet films is the critical myosil concentration. So this is defined as the concentration of surfactants above which agglomeration of myocels form. In addition, the surfactants added to the system add to myocels that previously exist. So generally for Langmuir-Blanchet films, agglomeration of myocels is not desired, it's to be avoided. So we have to watch the concentration and control that well so that we actually don't form myocels. So at a certain energy threshold, the myocel becomes thermodynamically more stable than the solution. So what the surfactants are going to do is look to minimize their energy, and they can do that by forming a lipid layer or a lipid bilayer. So in some applications we want that for say making liposomes or myocel drugs, but we don't want that for Langmuir-Blanchet films because we don't want to have this agglomeration to happen. So this is an example when we do have agglomeration. We can form materials like this that we studied in a different portion of this lecture series, and this is the liposome, and it's often used for drug delivery. So what we have here is a lipid bilayer, which is going to form over that concentration level, critical concentration level, and it's going to form into this thermodynamically preferential system. And what we can do at this point is put drugs in here and use this as the drug delivery system per se. So that's again covered in another portion of the class. I'll let you look that up into the notes and videos, but this is something that per se that we're trying to avoid, because right now in this part of the lecture we're concerned with films, so we don't want to form lipid bilayers or myocels. So what we're going to do right now is take a break. That's the end of part one. What we're going to do is come back in part two and look at different energies that drive self-assembly. We're going to look at surface energies of materials and the bonds that cause them. So I'd like to thank you for your attention and look forward to continuing this discussion in part two. Take care.